This is, oops, this is lab 10 on static equilibrium. Okay, so let's begin by first stating the two conditions of equilibrium. All right, so let's write down the first condition of equilibrium. Right? And the statement of the first condition of equilibrium is that when a body is in translational equilibrium, under the action of several coplanar forces, the vector sum of the forces is 0. Okay, and so what we expressing this in terms of mathematics, so we can say mathematically statement is that the sum of all the forces equals 0. And if we break up the forces into the x and y components, one can say that f sub x equals 0, comma, f sub y equals 0. Right? Another way, of course, of stating this is by saying the forces in the positive x direction must equal the forces in the negative x direction. All right, and similarly, the forces in the y direction, positive y direction, must equal the forces in the negative y direction. All right, so now let's talk about the second condition of equilibrium. All right. Now, this condition of equilibrium corresponds to the absence of any tendency of a body to rotate in the presence of all forces acting on the body. Okay, so maybe you should write that down. Oh, okay, this equilibrium, I'm trying to define equilibrium in this case, this corresponds to the absence of any tendency of a body to rotate in the presence of all forces acting on the body. Okay? And so the statement, the actual statement of the second condition of equilibrium is the following. The actual statement is the sum of all the moments or torques of all the forces on the body calculated, this is important, calculated with respect to some specified axis must be zero. Okay? In order to be in equilibrium. All right? And mathematically, the statement is and designating a torque by tau, the statement is that the sum of all the torques equals zero. And of course, you must put in parentheses about any arbitrary axis. The word arbitrary is important there. Okay? And torque is a vector. All right. Now you guys may not be discussing the vector aspects of torque, but it's a vector, and we won't be talking about torque as a vector either. All right. So let's make sure we all understand what we mean by torque. Okay. So here's an example. Here's an example. Let's consider a door. Okay. And so here's the hinge of the door, and here's a door. Okay, and let the length of this door be r. Okay, this is the door. Giving the top view of the door. So the axis, the wall to which it is attached and the axis about which it rotates is perpendicular to the page. All right. And so let's put this down here. I'll say this is the axis of rotation. This is the axis of rotation. All right. And so let's now apply a force Okay, I'm going to apply a force here. And let me define this angle that the force makes with the door. Let me call this theta. Okay, and let me extend this. This is the line. This is the line of action of the force. Okay, and let this be and let me erase that, and let this be the this is the perpendicular distance. I will call this distance from here to here. I'll call this R perpendicular. This is R perpendicular. Okay. So now the torque about, let's write this down. The torque about the axis okay, is the product of the force F and the perpendicular distance to the axis. From the line of the force. All right, since we've done line of action of the force. Okay, all right. And so what is the definition? The definition then is tau equals the product, and we're going to talk about magnitudes here now, a product of F times R, F times R perpendicular. Now R perpendicular from that triangle is nothing else but F times R sine theta. Okay. Now R perpendicular, let me write it down here, R perpendicular, which is equal to R sine theta, is called the moment arm. Okay? Now, it's also possible to define torque or to obtain torque in a slightly different way, okay? And let me show you the slightly different way of obtaining the torque, all right? So the first idea here is, let's go on to the next page. Let's redraw the picture. Here's my axis, and here's my door. Okay, and the length of the door is R. So let's get that down. All right. And here's my force F. Oops. This is my force F. Okay, and this is the angle theta. Put it in here. And what I do next is that I break up this force into a perpendicular component, which I will say is F perpendicular, which is equal to F sine theta, and a horizontal or parallel component, if you like, over here, a parallel component, which I'll simply call F parallel. F parallel. Well, okay, let me just call it F parallel. All right, it doesn't matter at this point. It's of course nothing else but F cosine theta. All right. So now one can define torque in an alternate way by saying that torque tau is now F perpendicular times the distance to the axis, which is r, and so this is equal to F perpendicular is F sine theta. This is F sine theta times r, and this of course is exactly the same expression as the previous page, which was F r sine theta. Just rewriting it, that's all. But what is interesting is that you get the same expression, and what is because and I will make this as a note. I will say note. Okay, the torque due to F parallel is 0 because it goes through the axis of rotation. Okay? There is no distance between this force and the axis of rotation. It goes through the axis of rotation, so F parallel, the torque due to F parallel is 0. Okay? And so you get the same expression as F perpendicular times the distance r. All right? So these are two ways of thinking in terms of torque or defining torque. There is a convention, and okay, there is a convention one has, which states that counterclockwise torques are positive, and that clockwise torques are negative. Okay? But just as in the first condition of equilibrium, it is much easier, it's the same thing, but you can think about stating the second condition of equilibrium as saying that the clockwise torques must equal the counterclockwise torques. So you can write this equation, all right? You can do that equation. All right, let's talk a little bit. Let's do an example. So here's an example, and I'm going to consider this the example that you're going to do in the first part of the lab. Okay, so the example is the following. You have a bar, and here's a fulcrum. Okay, this is the fulcrum, or the axis. Okay, and let's put a weight here, which is W1. Let's call the fulcrum to be at some point called O. Let's put a weight W1 at a distance X1, and another weight W2 at a distance X2. All right, so that's the problem. Now we want to use our conditions of equilibrium in order to determine various properties of the system. So the first thing to do, as always, is to draw a free body diagram. So let's draw a free body diagram. All right, so here we go. Here's my bar. Okay, oops, I didn't mean that. Sorry. Interesting what this Apple iPad will do. Okay, so here's my bar. Here's W1. This is the point O. This this well, let's draw the forces first. Here's W2. Okay, so this bar is sitting on this fulcrum or axis, and so the axis applies an equal and opposite force on the bar. The bar is applying a downward force on the axis, on the fulcrum, and so the fulcrum applies an equal and opposite force, okay, on the bar, and that I will call P. Okay, and then there's one other force. These two forces are something that we've added, but there's another force out here, which is the weight of the bar itself. Okay, and so let's let the action of the weight of the bar, I will call this W bar. Okay, and if I know the length of the bar, suppose the length of the bar is L, then I know that the weight of the bar can be assumed to be concentrated at the center of the bar. So the distance, so let's now write down all the distances involved out here. W1 is at a distance x1 from the axis. W2 let me put it over here, up here, W2 is at a distance x2 from the axis. Okay, here's the axis coming out of the page. Okay, and let me assume further that this distance from the center of the bar to the axis, let me call this distance L, lowercase l. All right. So now let's write down all the equations that we can for this system. Now we've got the free body diagram, so we can go right ahead and do this. Okay. So first, let's write down the first condition of equilibrium. That is, the sum of all the forces equals 0. All right. So, well, we have P is acting upwards. W1 is acting downwards. W bar is acting downwards. W2, this is W2, is acting downwards. All right, so that's your first condition of equilibrium. Now, so now we say, taking the torques about the fulcrum, okay, what is my equation? Well, let's do the counterclockwise torques first. Okay, so counterclockwise torques first. Well, W1, if you have the axis around O and you pull on W1, it's going to go counterclockwise. So that torque, counterclockwise torque, is W1 times the perpendicular distance, which is x1. The clockwise torques, the clockwise torque is 1 due to the bar first. If you pull down the arrow where W bar is, it will rotate clockwise, right? So it's W bar times L, which is the perpendicular distance, plus W2 times x2, right? If you pull on W2, again, this bar is going to rotate clockwise, okay? What about the torque of the force P? Well, the force P is going through the axis. So the torque of that force is 0. So now you can write down your torque equation. The torque equation then becomes, this then leads to W1 x1 equals W bar times L plus W2 times x2. So there are your two equations. All right. Finally, let's do another problem, which is part 4 of your lab, which I do not want you to do. So let's talk about it. The reason I don't want you to do it is because it's the same as part 3 of the lab. So there's no need for redundancy. This is purely redundant. Okay, so here's the problem. Here's the problem. Suppose I have a wall. Okay. And to this wall is attached a bar. Okay. And suppose there is a cable over here at a distance x from the wall and from the axis, therefore from the axis. And this is a cable. This is theta. This is a cable. And let's assume the tension in the cable is T. Okay? And I'm going to assume the weight of the bar is at the center of the bar. So this is W bar. And just like in the previous problem, let me assume this distance is L over 2. Okay, L being the length of the bar. So L over 2, and this is also L over 2. Okay, and we want to solve this problem. And we want to apply the conditions of equilibrium to this problem. And let's see. Let me first draw all the forces in this problem. Okay. So let's go back. Here's our wall. Let me do it here. And this is the bar. I want to draw all the forces on this problem. So first let me draw the cable and the tension T in the cable. This angle is theta. And this distance is x. Okay. We then have the weight of the bar, which is W bar. And this distance we have agreed upon is L over 2. Now, are these the only forces acting on the bar? And the answer is no. Because the bar is applying a force on the wall. Because of that cable, it's pulling on the wall, right? So if it's pulling on the wall, what does the wall do? The wall pulls back at it. And so there is another force. There is another force of the wall on the bar, unknown, and therefore the magnitude F and the angle alpha are unknown. Okay, we don't know that. So that's part of the problem that one has to determine this. All right, once one has done that, then the idea is, let's break this up into an x and y components, because that makes life so much easier. All right, so here I'm going to do that down here. Let's take this bar. Okay. Here's T. And I'm going to now get rid of it. So what I'm going to do is I'm going to say, this is T sine theta, and this is theta. So this is T sine theta. This is t cosine theta. Okay, so I've got rid of t, I've got in terms of its components. There is, of course, this w bar, which is downwards here. We know that this distance here is x, and this distance here is L over 2. Okay, and now I have this other force. Let's call this F. This is the other force. Now let me get rid of this force and break it up into its x component, which I will call Fx. This angle is some angle alpha. Who knows what it is? And this is Fy. So I've now got all my forces. This is my x, and this is my y coordinates. Okay, and so now I'm set to solve the problem. All right. So let's write down the first conditions of equilibrium. So the first condition of equilibrium, Fx equals 0. The forces going to the right must equal the forces going to the left. So we have t cosine theta, which is going to the right, must equal Fx, which is the force going to the left. Look into the condition F sub y equals 0. What's going up must equal what's going down. So what's going up, the force going up, is t sine theta, and this must equal all the forces which are downwards, which is w bar plus Fy. Okay, so here are two equations from the first condition of equilibrium. But notice that I have three unknowns: the tension and the x and y components of the force. Presumably I know the weight of the bar and I know the angle theta. Okay, now let's do the second condition of equilibrium, which is tau equals 0. So let's do, again, one must first define, taking moments about the axis at O, and so let's define this as O. This is O. All right, this point is O. All right, and so we have, let's do the counterclockwise. First, let's do counterclockwise. Let's see. You have, if I pull on t sine theta upwards, I have a counterclockwise torque. So that torque is t sine theta times the perpendicular distance, which is x. Okay, and if I look around, there are no other counterclockwise torques because the forces Fx and Fy go through the axis. Okay, so now let's write down what the clockwise and of course and t cosine theta also goes through the axis. Okay, let's look at the clockwise. The only clockwise, if I pull on the weight on w bar, this bar is going to rotate clockwise, and so that is w bar times L over 2, And so my my third equation, because I have three unknowns, must get three equations, is x times t sine theta equals w bar times L over 2. And so here's my third equation. Okay, so I have three unknowns, okay, t, fx, and fy, and now I have three equations, so I can determine all three quantities trivially, okay, and then with fx and fy determined, okay, I have f, magnitude of f is fx squared plus fy squared, and alpha is equal to arctan fy over fx. Okay, so we've determined all the properties of this system. Okay, so basically that's what your experiment today is all about. You have to use both conditions of equilibrium, important, and this will also give you an idea of how to use the torque equation, okay, for the second condition of equilibrium. All right, okay, take care, bye-bye.